So to recap what we're looking for, we were given a diagram, we'll find the tension in those two cables. We do expect them to be equal because of symmetry, but they don't have to be. And we want to find all the reactions at that ball and socket joint at A. So we chose the platform as our object of interest here. So I put the pertinent coordinates in A, B, and C. We have D, where the ropes are going to, at 0, 0, 3. I added a point E, and that's where we have this applied force of 300 newtons. So the other forces acting on the platform, we have the tension in the cable that went from C to D, and the tension that goes from B to D. And then what other forces or couples act on our platform. Right, so we have the ball and socket at A. The ball and socket prevents all translation, so we can model that as a force in the X, I'll assume is positive, a force in the Y, I'll assume is positive, and a force in the Z. The ball and socket does allow rotation about every axis, at least a little bit of rotation, so there's no couples. Right, so there's 5 unknowns in this problem. Usually, on average, we're going to see 6 unknowns. So I would say we would want to pause here and just reevaluate, make sure that we have modeled it correctly. But I will say there are 5 unknowns in this problem, so there are not a total of 6. Because remember, I have the equilibrium equations. We can get up to 6 linearly independent equations. But we'll see why, in this case, we're only going to get 5 in the end. So we'll have exactly enough equations to solve for our 5 unknowns in this one. All right, so before we get to the equilibrium equations, what will we want to find first? Right, unit vectors, so I'll just give you those. So we want B to D and C to D for each of our tensions. So in the x direction, we'll have the components from the tensions. So negative 2/7 TBD minus 2/7 TCD plus AX. In the y direction, we'll have 3/7 TBD minus 3/7 TCD plus AY. And the z direction, we'll have the 6/7 TBD plus the 6/7 TCD plus our AZ minus the 300 newtons from that applied force at what I called E. So from the force equations, we have 5 unknowns, 3 equations. I won't go through all the steps on this one, but we'll get the 3 other equations from taking the moments about a point. So what point in this one seems the most obvious? Right, the ball and socket at A eliminates AX, AY, AZ. So that's going to be equal to the 0 vector. I won't go through any of these steps for this one, but I'll write the equations that they give us because that is important for this. So we go through all that, we pull out the I coefficients. We're going to get that 0 is 1.29 times TCD minus TBD. I'll write equation 5 up here. So with the J coefficient, 0 is 300 minus 1.29 TCD minus TBD. Okay. And for the K coefficient, we get 0 is negative 0.214 TCD minus TBD. So it appears at the moment we have the 5 unknowns from our free body diagram. We have 6 equations from the equilibrium. None of them are 0 equals 0 like we sometimes see in our examples. However, what can we say about these 6 equations, though? If you look at equation 4 and equation 6, what's the difference between the two?
Coefficient.
Right, so all they do, if we multiply equation 4 by a scalar, we get equation 6. So that's the easiest way we could have two equations that are not linearly independent. Sometimes it's tougher to tell, and you would have to use some matrix methods. But here, all I have to do is to multiply this by like about negative 1/6 or so, and we get equation 6. So if you have a linearly independent means we can't take any other equation, or we can't take the scalar multiple of any other of our equations, add them together, and make one of the equations we have. So if we look at 4 and 6, that's not true. We can multiply this by a scalar, and we can get exactly equation 6. So 4 and 6 are really the same equation. It's redundant. So we can get rid of one of them, and we don't lose any information, because 4 and 6 tell us exactly the same thing. So for the sake of argument, I'll choose 6. I could have just as easily said 4 was crossed out. So now I have 5 linearly independent equations for my 5 unknowns. Now it's a solvable system. Again, 6 and 4 tell us the exact same thing. So equations 1 through 5 we can use for our 5 unknowns. Now if we solve these, I'll give you the answers. We do get mathematically that the tensions are the same, which we expected, but wasn't necessarily true up front. The tensions are 117 newtons. They're both positive, so that's our initial check. The X component at the ball and socket is 66.7 newtons. The Y component, we get 0. And the Z component, we get 100 newtons.